Webinar on smart investigations for pumped hydro projects, fast, integrated, and cost-effective approach. Thank you for taking the time to join us. We are thrilled to have participants across varied backgrounds and geographies with us here today. Before we begin, just a few quick housekeeping points. Those who are regulars will be familiar with this by now, and so please bear with me. But those who are new here, please take note. We request all participants to please post their questions in the chat box as the session progresses. This will be addressed in the question and answer session at the end of the webinar. The presentation slides, recordings, and the related materials, everything related to the webinar, all resources will be shared with the registered participants through the official WhatsApp group, the link for which has already been sent to you via email. If you haven't received the link, then don't worry. We will also post the link again in the chat box. Now, coming back to our webinar, pumped hydro storage projects are among the most complex infrastructure systems. They involve large project areas, geologically variable and heterogeneous systems, reservoir rims, and deep underground works such as tunnels and powerhouse caverns. Many critical features such as fracture zones, shear zones, buried valleys, and potential leakage paths are often not fully captured through conventional investigation methods, and this can lead to significant uncertainties during excavation. Today's webinar focuses on how integrating geophysics with engineering geology can help provide a more continuous and reliable understanding of subsurface conditions, supporting smarter investigations, better planning, and more informed decision-making. We have two excellent speakers with us today, Dr. Sanjay Rana from Parson Overseas Private Limited and Mrs. Mugdha Patwardhan, an expert in engineering geology with more than 15 years of experience in hydropower and infrastructure projects. Dr. Rana, a pioneer of engineering geophysics in India with over 3 decades of experience, will discuss how multi-method geophysics can address key challenges in pumped hydro projects. And Ms. Mugdha Patwardhan will bring in engineering geology perspective, focusing on interpretation and integration of data to develop robust geological and practical models. So with that, let us begin. It is my pleasure to invite Dr. Sanjay Rana to start the session. Over to you, Dr. Rana.
Thank you, Suchetna, for that introduction and for setting the context so well. And a warm welcome to all the participants. Before we begin, I would like to acknowledge the team working behind the scenes who have made this webinar possible. These efforts often go unnoticed, but they are absolutely critical in bringing such sessions together smoothly. Mr. Rashik Katuria, Ms. Anushka Batra, Ms. Priya Mohini, Ms. Suchetna Banerjee, and my fellow speaker, Ms. Mugdha Patwardhan. So thank you for your efforts in bringing this session together. And my sincere thanks to all the participants who have joined us today. Thank you for investing something extremely valuable, and that is your time. And we deeply respect that. So our effort today will be to make this session as practical, insightful, and meaningful as possible. Let me begin with a very simple thought. In PSP projects, the success or failure is rarely decided at the surface. It is decided deep within the ground, often hundreds of meters below, in conditions we do not directly see. Weak rock zones, shear zones, water-bearing structures, geological variability. These are not visible, but they control performance, safety, and cost. And that leads to a fundamental challenge. We are designing these large underground systems, while a significant part of the ground remains unseen and only partially understood. Traditionally, we depend on boreholes and limited investigations, but the ground is continuous, while our data is discrete. And the biggest risk often lies between these data points, between these discrete data points. And this is exactly where engineering geophysics becomes extremely powerful, because it allows us to move from point-based understanding to continuous subsurface insight. So in today's session, I will focus on how geophysical investigation can help us better underground PSP projects, particularly in identifying critical geological conditions, optimizing investigation, and reducing uncertainty in deep underground works. And then Ms. Mugdha Patwardhan will take this forward and bring in the engineering geology perspective, connecting these insights to practical design, interpretation, and decision making. She will also take a few beautiful case studies of pump storage projects. So with this, I would like to begin my presentation. Okay, right. It's a ritual to check with Rashikji. Everything okay, Rashikji?
All good, sir.
All right. So today's webinar is on smart investigation for pumped hydro project. As we talked about, we are going to talk about fast, integrated, and cost-effective approaches using geophysics and engineering geology. And I will just unshare it once and then share it again. That's also a ritual for me for some reason. Okay. There we go. Right? Everything okay, Rashidji?
Yes, sir. All okay.
All right. So this webinar and this series of webinar is being brought to you by Parson. Parson is a geophysical company. We are known for bringing various technologies in the country from time to time. The list is there. I'm not going to read through it. Our strength is in innovation and trying to bring the best from the world to the country. Main strength, of course, is our people who are highly experienced with a number of doctorates and most masters. We are an Indian multinational, so we have office in India, of course, that's our head office, and Bahrain, Saudi Arabia, and Singapore. And through these offices, we are working in 14 countries around the world. I am a geophysicist by profession. I graduated in 1990 from University of Roorkee, which is now IIT Roorkee. So it has been 36 years now. Initial 5 years I spent with the government, and in 1995 I took the plunge and become an entrepreneur. And since then I'm just doing this geophysics, mostly near surface geophysics, and have worked on a number of hydropower projects, including India, Afghanistan, etc., and a number of pumped storage projects. I'm also working on development of codes and practices and standards, including Bureau of Indian Standard, Indian Road Congress, Tunneling Association of India, etc., etc. There are few guidelines which already have been authored by me, including on dams, on tunnels, on bridges, and on subsurface mapping. So that was it about introduction. So coming to the topic right away, because as I said, we value your time and time is limited. So we will go a little quick. We'll try to cover a lot with a promise that whatever questions you have after that, we will take the questions right here. And even after that, later on through email, we are always connected. So when we define investigations, it can be defined as a methodology of acquiring advanced knowledge of the site conditions so that a techno-commercially viable project layout can be developed, right? So this is how we can define investigation. And it is very well known that good quality of investigation, good quantity of investigation, and good time allowed for investigations lead to less uncertainties and less cost and claims. So this is something which is very well documented, not only in India, but across the world. In very famous words of Shri Visvesvaraya, he said the engineer's first problem in any design situation is to discover what the problem really is. Idea is that you should be able to define your problem correctly, do the investigations, and most importantly, avoid assumptions. Avoid assumptions. In general, in life also, we always say avoid assumptions, measure, calculate. But what actually happens in most of the engineering projects is that we are depending largely on drill holes. And between drill holes, what exactly is happening? We are assuming. So everything in between the drill holes is actually unknown, and we are just making assumptions. So we think that the formation, what we have encountered here and encountered here, we can just connect these through lines. Is that really valid in complex geologies or any kind of geology for that matter? So the ground between borehole is inferred, not observed. Risk of wrong assumption is very, very high. And that's a fundamental mistake which we make in almost all the projects. It can be tunneling, it can be pump storage, it can be any project we are putting. And then we come across something which is termed as a geological surprise. Fact is that expertise and engineering solutions are available for dealing with almost any ground condition. You are doing tunneling and you know that there is an aquifer which you might encounter or a loose zone which you might encounter. You can do pre-grouting and actually go across it. Problem is meeting the unexpected and uncertainty of the ground condition. That is, we suddenly come across something which we did not expect. That is what it is. So geological surprise is nothing but a situation which was not anticipated because ground was not investigated properly. That's the right way of putting what is a geological surprise. And if you look at just the data, right, statistics, this is coming from International Tunneling Association. It's a very, very beautiful statistics I refer to in most of my presentations. It says that even comprehensive exploration program recovers a relatively minuscule drill core volume that is less than 0.0005% of the future excavated volume of the tunnel. Wow. And this is equivalent to one vertical 100 diameter borehole for every 100-meter length along a 5-meter diameter tunnel, etc., etc. Right. So this is a statistics. It can be calculated, right? So we just have this 0.0005% information if we are depending only on drill holes, even if we are doing it comprehensively. When we say comprehensively, we are talking about spending around 5% of the budget on investigation. What is the average in India? How much money do we spend in investigation? Can anyone write in the chat box, please? What is your assumption? How much percentage of the project cost we are spending on investigation? Let's take a guess in the chat box quickly. Let's take a guess how much we are spending. Interesting. So whoever is saying 3%, 5%, I really say that you are really optimistic about how the things are going on. We are actually spending on an average 0.75%, that is less than 1%. There are a lot of replies which have come less than 1%. That's the right reply. We spend around 0.75% of the project cost towards investigation. That is 1/10 of the global average. So actually you can add one more zero in the uncertainty here. It will become 0.00005% of the actual excavated volume. Now that is what the information we have. And with this information, we make our decisions. We make our design decisions, right? It is no better than making decisions with your eyes closed. So we cannot really call ourselves a smart decision maker when the information available is so small. So totally incomplete information, hidden risk, uncertain outcome, complex conditions. That's what we are dealing with if we are depending only on drill holes. So the investigation, when we are talking about, the next question is, in that case, how much should we do, right? Can we actually turn ground into Swiss cheese? Of course not. You cannot drill every 1 meter, every 2 meters, right? That's impossible. So what's the solution? And that's what we are talking about. The solution comes in terms of geophysical investigations. Geophysical investigations are the one which give you continuous subsurface information, all right? And they can detect hidden features, variability, and reduce uncertainty a lot, all right? Geophysical investigations do not replace drilling. This is a very important message I want to convey right in the beginning of this talk. They do not replace drilling, not at all. They help you target drilling, they help you optimize drilling, and they help you give continuous information between the drill holes. That is what geophysics does. There are a few dialog boxes. I'll just, okay. So for the uninitiated, those who are attending this kind of geophysical in a talk for the first time, if I have to explain what we do in geophysics, I always compare it with medical science. So in medical science, you have different imaging methods to reveal what cannot be seen from the outside. That is, you do X-ray, you do MRI, you do CT scan, you do ultrasound. What you are doing is you are sending different kind of rays and waves inside the human body to understand what's inside the human body. Same thing we are doing in geophysics. That is, we are sending different kind of rays and waves inside the earth or a structure to find out what's inside the earth and its structure without drilling, without digging. So that's basically the best way to understand what we are doing it. In geophysics, we of course also measure the naturally occurring fields like magnetic field, gravity field, telluric field, etc., etc. But this is a very good way to understand what we are doing here. As a science, it falls at the intersection of geology, physics, and maths and computer science. So that's where geophysics falls. So one needs to have a good understanding of all the disciplines, all these disciplines to be a good geophysicist. So the question why use geophysics is answered by this simple analogy with the medical science. Why use geophysics is why use X-ray, why use CT scan, why use ultrasound. Low cost, rapid coverage. These days, you can do hundreds and thousands of kilometers in a single day, for example, using heliborne and airborne techniques. Continuous information, the biggest thing. For example, you look at this diagram here. There's a void, there's a limestone pinnacle, there are few anthropological features, there's a fossil. What are the chances that only drilling will be able to detect all these features? 1 in 1,000 or 1 in million, depending on the size of the object and the spacing of your drill holes. Geophysics, on the other hand, can give you continuous information, and that can lead to optimization of drill holes, not elimination of drill holes, because geophysics and geotechnics give totally different things altogether. It's very important to do drilling to understand the material as it is, because what you're getting in geophysics are physical properties, seismic velocities, resistivity, etc., etc. Drilling is must, but optimized drilling, not random drilling. So it's just like you going for laparoscopic surgery. You first do imaging, you do ultrasound, you do MRI or whatever, and then you do the laparoscopic surgery. If you don't have this image, you'll keep drilling inside the body everywhere and still not find the stone which you are trying to remove. And this leads to minimization of surprises, and it's always good for early stage application. Okay. Most important thing which is being missed today as geophysics is becoming more popular. Thankfully, many practitioners are coming. Thankfully, many clients are also adopting it, but unfortunately not in the right way. There's a 7-step framework of geophysics, which starts with setup, where we understand the objectives, then contrast which physical property will have best contrast between host and the target, then design the survey, and then go for data collection. Today, what has happened is, just because one particular method worked well in project A, we just copy paste the same BOQ for project TOR for project B. Doesn't happen like that. Geology is different. The methods have to be chosen carefully based on the objectives. Then data collection, processing, interpretation, and then synthesis. Combine the interpretation with prior knowledge about the problem with other relevant information, drill hole data, geological maps, remote sensing data, whatever. Decide if your results are adequate for the particular problem, and then decide further investigation if needed. Unfortunately, top 3 and the last step are being missed in most of the geophysical campaigns today, which leads to frustration for the client. Coming to PSP site investigation, right? Because this part was just about geophysics. Very important to understand this before we dive into PSP directly. So once we are talking about
global
PSP site
electricity demand experiences
introduction to
daily
PSP.
variations. Energy management is vital during peak times. Pumped storage hydropower uses 2 water reservoirs. The other reservoir
Can someone confirm whether the video audio is there?
Yes, it is there.
acts like a rechargeable battery. A penstock serves to connect 2 separate water bodies. During off-peak hours, water is efficiently pumped up. Excess grid energy drives the powerful pumps. Energy is stored as gravitational potential energy. When demand rises for water, it is released back. Falling water spins turbines to generate electricity. This cycle provides a reliable, repeatable loop. Grid stability and sustainable energy management.
All right, so this was just a very, very basic video because there are many students who also join these webinars, so it's important to understand. So PSP projects pose a different challenge altogether because the area covered is large. So large scale, because massive infrastructure and footprint. Caverns can go pretty deep, and geology can be complex. So these are challenges which are unique to PSP project because the reservoir area sometimes is very, very big. Caverns can go up to even 400 meters, 600 meters at time, right? So this is a different challenge altogether. So we investigate points, but design for volume. So in PSP projects, these are big areas which we are covering. And if we continue just investigating points, that is sparse data with limited sampling and a lot of gaps and uncertainty, that's a big problem because we are designing for volume where conditions are different, variable. So the investigation steps when we talk about for any project, they generally start with study available geological maps, remote sensing data, satellite images, etc., etc. Geological mapping, very, very important. And then the next step must be geophysical investigations before drilling. That is the right sequence. Because if you are drilling randomly, you are not utilizing the full potential of geophysics. So geophysical investigation, then drilling, and of course, slope stability, hydrogeological, seismic study, borrow area study, other site-specific investigation, it can follow. The main message is what is where the geophysics falls in the entire sequence. It falls before drilling, not along drilling, not after drilling, before drilling. So you can optimize your drilling and do drilling right at the places where you get the best data out of it. Because it is expensive, it is slow, it is time consuming. So you have now in PSP also, it doesn't change regional understanding. So you build a geological conceptual model using maps, remote sensing, and existing data. Go to surface geophysics, then go to targeted drilling, then go to investigations for deep caverns. They can be based on boreholes. They can be done from the tunnel to surface, between the tunnels. We'll talk about it. And then the validation. So this is the flow for PSP, which is very important to understand in the beginning. A validation is validate and integrate all data for reliable design and risk mitigation. So this is the complete flow how it ideally should go in PSP. I will just list down 5 or 6 objectives of investigation in PSP project and then go how different methods achieve these objectives. First, of course, is ensuring a safe, stable, and durable dam foundation, right? Where you're looking for geology, where your dam is coming up, your other structures are coming up to see the strength, water tightness, etc., etc. So this is one objective. Then you have reservoir area after dam completion, the entire reservoir area which you're going to cover, whether it is watertight, whether you have any lineaments there or any such zones through which the water seepage can take place. Because remember, PSP projects are coming in areas which have not seen water. How they are going to interact with water is really unknown, right? So it's very, very, very important to understand what is the water tightness of these areas, how these areas are. Then slope stability. Slope stability of the rim area to prevent landslides, which ultimately can create waves and can completely disrupt your entire operation. Then deep powerhouse caverns. This is an investigation challenge, right? Because your depth can be large, your variability can be high. So how to investigate your deep caverns? Then you have water conductor systems, which, as we have seen, are linking your upper reservoir to the lower reservoir. The terrain can be very steep, very, very steep terrain, right? There can be, extreme elevation differences, but very important to investigate. Then you have material sources for dam construction, right? You have core material, shoulder material, etc., where this material can come from the nearby areas, identifying the right material in the subsurface in these areas, another objective. And then, of course, you have hydrological studies, foundation design, environment impact, seismic hazard assessment, construction planning. Most of the objectives I could think of. You can add maybe 5 more objectives to it. Doesn't really change anything. Because what we are going to talk about practically addresses to all the objectives which we have in investigation of PSP projects. So what all geophysical methods are available for this? Let's go to that quickly. Before we go to that, I'll take a 45 seconds break. Why I'll take this break is that I'll announce the next webinar, which is scheduled on June 6th, 2026. We are doing this webinar every month. So this is on weak and leaking dam foundations. I have done a number of webinars on dam structure health monitoring. This one is focused on weak and leaking dam foundation below the dam body. So please scan this QR code right now. I'm giving you 35 seconds for that. The 10 seconds I've already consumed out of my 45. So just scan this QR code and it will take you to this link, which is there, Dam Foundation. You just have to put your name, your email ID, and your number, and you'll be registered. It is 10 seconds process. So let's do it quickly, please. We'll resume in 20 seconds from now. Let's do it quickly. All right. I hope everyone has done it. So we can resume the session. All right. So first method, which is very, very useful for PSP projects, is seismic refraction tomography. Now, in seismic refraction tomography, we are sending seismic waves inside by using a source. For shallow investigation, 25, 30 meter, it can be just a 10 kg sledgehammer. For deeper investigation, we can use weight drop or explosives if it is allowed. And these waves interact from the subsurface. I'm not going in any technical detail, and basically give you a compressional wave velocity model of the subsurface. That is P wave. P wave is directly linked to the strength of the subsurface. So, for example, if you have very good rock, it will have higher P wave velocity. If you have weathered rock, it will have a lower P wave velocity. Soils will have even a further low P wave velocity, right? So it gives you this subsurface imaging for different depth and rock layers, fault and fracture detection, site stability, and a very, very important tool to support your design later. These are few examples. So this is, you can see around 450 meter of length, 900 to 800, so around 100 meter is the elevation difference here. And this investigation has been done, and all this red which you see is good rock. All this green which you see is basically weathered rock, and all the blue which you see is the overburden, that is the soil. So like this, you're able to see the complete topography of your rock layer, how deep it is going at different places, etc. Quick survey, very good to understand the strength of the subsurface. And then you can obviously demarcate the interfaces. So you can see again here 0 to 115 meters. This is how your weathered bedrock interface is changing. This is a top, and this is a weathered bedrock, and this is your hard bedrock here, right? So like this, you get the complete image continuous. It is not discrete, so you do not miss these kind of low velocity zones. This is a small shear zone which is there, which you do not miss, especially now in seismic refraction tomography, which is conducted, right? It's very, very strong method for understanding the subsurface. So what it gives you is bedrock profile, rock quality, and depth. So you understand subsurface structure and competence, thickness of overburden, fracture and weak zones, slope stability studies, because you have the subsurface conditions, including thickness of overburden, weathered rock, etc., etc. Very strong technique. One of the techniques I'm going to talk about. Second is electrical resistivity imaging. So as I always say, why so many methods? So you have X-ray, you have ultrasound, you have CT scan. Why so many methods in medical field? because every method is giving you a different property. So for different objective, you use a different method. So similarly, when we are talking about the strength, we use seismic methods. When we are talking of things which are controlled by moisture or water, we are using resistivity method. So it tells you water bearing formations, rock lineaments and fractures, seepage prone areas, dam foundation integrity, understand the hydrological conditions. All this comes from electrical resistivity imaging. Again, a complete 2D picture. And this is a very beautiful example of application of ERI in a PSP project. Ms. Mugdha will deliberate more on this in her case study. But this was done in a reservoir area, and you can see these were the lineaments which were detected beautifully using ERI. And as I said, she will talk more about it, so I'm just leaving you with the importance of ERI in understanding your reservoir water tightness, for example. This is a beautiful case where a shear zone was detected using ERI for a tunnel project. Like this shear zone was expected based on a geological study. And initially they tried drilling. Of course, drilling will not give you these shear zones. So geophysics was done. This was done in a 1 day, 2 or 3 profiles, and shear zone was detected. So this is a very strong technique which find anything in the subsurface in which there is a change in moisture or water content. And how it helps you target drilling, this is a beautiful example of that. So this is around 1500 meter to 2500, around 1 kilometer of a stretch, and ERI has been done. 2 zones of low resistivity have been detected, and based on this investigation, drilling has been planned to puncture through these zones to study them more in detail and get their physical properties. That is how geophysics should be used to optimize drilling. The way we do it today, we'll keep drilling every 100 meters or 200 meters, and chances are that we'll miss these zones because these are very small zones. Might be completely missed by drilling alone. You can also do ARI across flowing water. So this is and this is not something which we did yesterday. We did it in 2001. This photograph on the top is from Karnali project in Nepal, where we did ERI across flowing water. And this was the bedrock, and this is a river water. So it can be done even in water. Even seismic refraction can be done in water. We just need a different source for that. We need hydrophone instead of geophone. It is possible. And this shear zone was completely missed by drilling. So extensive drilling across the proposed dam axis failed to detect the shear zone due to its narrow width and complex nature. And this was detected by ERI, which just took around 5 to 6 hours. All right. And this was almost a finalized dam axis. Imagine if actually execution had started, what kind of cost and time overrun would have happened. Then we have MASW, multi-channel analysis of surface waves. So seismic refraction gives you P wave velocity. MASW gives you shear wave velocity. Two very different formations can have the same P wave velocity. Saturated sand, clay, extremely weathered rock, even quicksand, all will have P wave velocity of 1500 meter per second. But once you add shear wave velocity, shear wave strength into the parameter, quicksand will have almost no shear wave passing through it. So it's very important because shear wave velocity gives you stiffness and elasticity. It helps assess ground support for large structures, and it is always an input into your seismic hazard studies. Whenever we are doing liquefaction study, etc., we always look for shear wave velocity. So very, very strong method again. This is how we get the shear wave velocity of the subsurface and then translate that into your geological model. This is and variation of MASW is refraction microtremor, REMI. Again, using the dispersion curve of Rayleigh waves, where you can depth can go up to 100 meters, and you can. This is a rock interface, and this is a very very loose, low shear wave velocity zone on the top. Combining of method is a very important thing to do. So this example shows a GPR and MASW combined, and ultimately geology inferred here, right? So once you combine methods, your confidence increases because, as I said, two different materials can have exactly one physical property which is the same. Coming to deep caverns, which is very important topic for today. That is what I promised that I will talk about it. Here, our depth can be pretty large. Surface investigations might not give you information up to that depth, or might not give you information up to that depth with the desired resolution. Remember, as we keep going down with our methods, resolution decreases. So here, boreholes will give you very sparse data. Critical decisions are based on this. So there is room for zero error once we talk about deep caverns. And that's where seismic tomography comes in picture. So seismic tomography can be done between any two available faces. So for example, if you have a tunnel and a top, you can do tomography between tunnel and the top to illuminate the entire ground in between. Or you can have boreholes and you can conduct tomography between the boreholes and have the complete information between these boreholes. And if you do it number of boreholes, you can practically have a 3D subsurface imaging. It will identify complex features like fractures, voids, heterogeneities, characterizing rock mass for safe and reliable design and improved decision making. So seismic tomography is the answer for your deep caverns. And these are few examples. So these are the drill holes S1, S2, S3, S4, S5, and seismic tomography has been done between them. And now you have a continuous picture. And even this fault here has been identified based on tomography. Just by drilling, you will not be able to identify this. But once you have continuous data, now you're able to see the entire geology. This is an example of a prestigious project we did in Bhutan. I'm very proud of this project because here our depth, here you can see 235 meters, right? Actually, boreholes were drilled much deeper. This section shows only up to 235 meters. And distance between borehole at one time went as much as 120 meters. Here you can see 120 meters. And idea was to map a cavity which had developed there. So this was 60 meters by 85 meters at one particular point. Very high resolution imaging you can do of your deep structures. Again here, around 235, and these are the voids in the subsurface, cavities in the subsurface. So seismic tomography gives you a tool which can be used to investigate your deep caverns. Not only between boreholes, but anything in which you have two faces available. I'll show you the example. Once you have enough data, as I said, you can convert this whole thing into 3D. So this is this example of the same cavity. You can see number of boreholes were there. The top platform was very small, 20 meters by 20 meters space was all what we had available. So we made one borehole in 30-degree inclination. Remaining boreholes were vertical. As you can see, all the borehole locations are in white. And then we did this tomography. And I'll just forward it a bit to show you how here. Now you can cut this 3D volume in any direction to actually see how this low velocity zone of the cavity is going. This is a top view here, how this is going. And then you can do obviously the volumetric calculation also. In this case, it was done to see how much grout will be required to fill this cavity. Okay. So very strong technique for these kind of investigations. This also can be done anywhere, as I said, where two faces are available. Recently, we did a couple of projects where we have done between twin tunnels to characterize the rock mass between the twin tunnels. You can do it between the drifts. So here are the drifts. This we did recently in a project. So drifts are there. And now in between these drifts, we did the tomography. So here, sensors are fixed on the top, the roof of one drift. So sensors are fixed here and the hammering will be done on this drift. Here is a person sitting with the equipment to do and here is the result. So this is one drift, this is a second drift. And now you can see the complete low velocity area is very clearly visible in the results here. This is the high velocity area, this is the moderate, and this is the low velocity area. So any two faces or surfaces when they are available, you can do tomography. So in case of PSP also, if you have a tunnel, you have a top, you can do the complete investigation between these to find out the complete characteristic between these two faces. So now link the geophysical techniques with what it delivers. I'm not going to read through the entire slides, and there's enough material on these slides to actually treat them as notes. All of this will be shared with you after the webinar, provided you are in the WhatsApp group. We will only and only share in the WhatsApp group. So if you have not joined, Miss Suchetna will put the WhatsApp group link in the chat box. Please join now. If you do not join the WhatsApp group, you miss on this information and much more information, which we'll keep sharing from time to time. So dam foundation in geology, SRT, MASW, ERI. These are the methods which we discussed, which give you bedrock profile, depth to bedrock, etc. Reservoir area, ERI, SP, lineament mapping by satellite, drone, and GPR. Slope stability, MASW, SRT, ERI. Deep powerhouse caverns, seismic tomography, surface-based or tunnel-based. Water conductor systems, seismic tomography, ERI, GPR for shallow targets. Material sources, again, ERT, MASW, seismic refraction. So whatever objectives we defined in the beginning, we practically covered all the techniques, and combination of techniques need to be applied to meet all these objectives, right? And the decision impact is huge. You might have to rethink of your alignment to avoid the weak zones. You have to rethink about the support for effective support based on rock mass quality. You can grout the weak zones in the fractured or low velocity zones. All these are measured impact on design. And once you do this, very small investigation cost can lead to a lot of saving in the failure cost. Failure cost is very high. Whenever you meet with unexpected, it is very risky and expensive. Project delays, reputation risk, and huge amount of money flows at this stage of a project. And all of us who are experienced enough know that sometimes we go to 200, 300 times, 300% of cost overrun. Time overrun is almost double anyway. All right. We can always avoid that by investigations. Faster investigations, faster projects. There are cases of failure of geophysical methods also. That's very important to understand. Right in the beginning, I said it's a 7-step process. Most of the time, the 7-step process is not being followed. Client just copies, paste from one tender to the other, or even the consultant, without understanding the 7-step process, proposes a particular method which might not be applicable in that case. So inadequate planning and survey design is the biggest reason of failure. Wrong tool selection is equally linked to inadequate planning, but a very big reason of failure. Method lacking desired resolution. Someone will ask me up to what depth you can do ERI. I will tell him ERI today can be done up to 300, 400 meters also. But the bigger question is, what is the resolution of ERI at 400 meters? You cannot detect small meter thick features at that depth. You need tomography for that, right? So method lacking desired resolution, geology ignored, only single tool used, never do that. Technological failures and data processing and interpretation error. This is becoming a new class of failure today. Because earlier, geophysical data was interpreted only by qualified geophysicists. There was no other way. Today, we have got this software. You put any data in there and you always get some color plot out. Now, that's a big risk because this kind of processing and interpretation is not involving the expertise which is required to actually process and interpret the data. So this is another class of error which is becoming very prominent. So this was my last slide practically. So when we do this, we don't reduce risk by drilling more. We reduce risk by understanding better. That's something which is very important to understand. Today, we feel that if we drill more, we have done more investigation. Incorrect. If we drill smartly, optimizing it after a good geophysical investigation, that's how we are basically reducing the risk. So see more beyond the eyes, understand more beyond the data, and reduce risk with confidence, deliver more with certainty. Very short, quick presentation I wanted to make, but I'm always open to receive any queries from you at any point of time. My email will be shared to you. Keep writing to me. And before I go, if any one of you want to meet me and other PSP experts in person, there's a good opportunity brought to you by Mission Energy Foundation. They are doing this pumped hydro storage conference on 11th and 12th June 2026 at Scope Convention Center, Delhi, where you get to meet a number of people, meet, network, collaborate, connect with the industry leaders, PSP experts, and key stakeholders. It's a great opportunity. Ms. Suchetna will put the website and the concerned phone number in the in the chat box. Please feel free to visit their website and physically meet people there. And now I would like to hand over the next part to Ms. Mugdha Patwardhan. She's a consulting engineering geologist with over 15 years of experience in hydropower and infrastructure projects, specializing in geological investigations for surface and underground works. She's MSc in Applied Geology from IIT Roorkee and has worked with leading organizations including Indo-Canadian Consulting Services, Parson, along with serving as co-founder and director at Upstairs Software LP. She has vast experience in geological mapping, geophysical data interpretation, and preparation of technical reports such as DPRs, GBRs, and GARs. She has contributed to various projects across India, Nepal, Bhutan, and Democratic Republic of Congo, and has been providing consultancy services to reputed firms like SMEC, Tractable, ICCS, and DDAG. Additionally, she has academic experience as a guest faculty for geology for a student of civil engineering at SGSITS Indore. And I had the privilege of working with her for a few years. She is a brilliant geologist. And the example I have shown you about all this 3D cavity moving, etc., etc. Mugdha was an integral part of that project. That's the time actually she joined and she just got stuck in the project, the first thing. So with this, Mugdha, I'll invite you for the next part of it. Welcome.
Yeah, thank you so much, sir. Okay, let me quickly share my screen. Please let me know if it's visible. Hello?
Yeah, it is visible, Mugdha.
Yeah, okay. So let me make it full screen. So as Sanjay sir introduced me, I've been working as a consulting engineering geologist for quite a few years now, and I've been dealing with PSPs for last 5-6 years. And even when I was working with the run-of-the-river schemes or any other hydropower project, the integral part of a geologist's job is, putting all the pieces together into the geological model of the project. Now, what are these pieces? These are basically the data which you acquire from different investigation tools. The foremost being the mapping, then all the subsurface investigation, which you plan and then carry out during the development stages of the project. So all that information is acquired, it is analyzed, it is understood, and then the proper geological model of a site is to be developed. That is the ultimate aim of any geologist working for any project for that matter. Now, I'll quickly run through what are the pump storage projects. Sanjay sir had already shown you one short video. Those who couldn't understand it, I'll just give you, I'll tell you in simple words what PSPs are. These are basically a hydroelectric energy storage technology. There are basically two reservoirs, one at a higher elevation, the other at a lower elevation, and the water keeps flowing in, from to and fro in between these two reservoirs. During the peak time, when the energy requirement is, or when the electricity demand is very high, the water flows from upper reservoir to the lower reservoir, and electricity is generated in the powerhouses and is supplied to the grid. On the other hand, when there is a lean time or when the demand is very low, the extra or the surplus electricity which is available on the grid is utilized, and the same water is once again pumped up from the lower reservoir to the upper reservoir. So this process keeps on going in loops, and that is how the PSPs work, and they are quite helpful. I wouldn't go into the technical details because that is not the topic of today's presentation. But I just wanted to give you a brief intro. Now, luckily, India has been blessed topographically, and India has got very good geographical features where these were ideal sites for setting up pump storage projects are available. For example, Vindhyans or the Deccan Traps, where there are a lot of remnant hills. Then there is Western Ghats or the Nilgiris. These are all ideal places for setting up PSPs, because what you need some higher platform for creating one reservoir and some lower ground for creating the lower reservoir. So wherever these are available in the vicinity, you can set up a PSP. So I'll give you quick definitions of the types of PSPs. The on-stream PSP is basically the one where both the reservoirs are built on the existing nalas or streams or rivers. Then off-stream open loop PSP is one where the one of the reservoirs, either the upper reservoir or the lower reservoir, is developed on any of the existing stream, and the other one is developed away from it. I mean, anywhere else. It is not connected to any water source. And the off-stream closed loop PSP is typically the one where there is neither of the two reservoirs are located on any river or stream. Both of them are away, and one time water is fetched from any nearby river or a reservoir, and both these reservoirs are filled up, and then they keep on working in the loop. Now I'll quickly go through the general um, list of geological investigations which are carried out for PSPs, the different components of PSPs. In the previous diagram, you must have noticed that the most important components are the reservoirs, right? Both these two reservoirs. They have to be huge. They have to be watertight, right? We cannot afford the loss of water. Secondly, there has to be a water conductor to, for taking the water to and fro from the two reservoirs. Then there has to be a powerhouse to generate the electricity. So these are some basic components of a PSP. They vary from place to place, but this is the general listing of the different components of any project. And as per the CA guidelines, these are the investigations which are suggested to be carried out for the different components. As you can see here, geological mapping is integral. It is a first step. Nothing works without a proper geological map. Followed by different investigations, which include the subsurface investigations, field investigations, lab investigations, and all the different kinds. Since today's focus is on the geophysical survey, you can see here geophysical surveys have to be carried out for almost all these dam components, the project components. Okay. Let me quickly get the lesson. Yeah, I've got it now. Okay, so these are the all these tick marks show the requirement of geophysical surveys for different components. Now, how do we proceed by the geological investigations for any project? Everybody, most of you must be aware, those who are practicing geologists or those who have been working with geologists, those who are engineers. The first step is always the regional studies, followed by the actual field geological mapping. And I have put them in double inverted commas, the good and reliable geological map. Remember that these two adjectives are very important because a map has to be reliable. Otherwise, you just cannot, move ahead with the project development. So spend as much time on mapping as possible. Do as detailed mapping as possible to create a wonderful and reliable geological map. And the map is often progressive in different stages of the project development. You keep on getting additional information and you keep on adding it on the map. So I believe a map has to be progressive. Secondly, planning of the investigations, all the subsurface investigations is based on that geological map. So you can understand the importance of the mapping. And then the subsurface investigations. Once you have a good map, you figure out what is where in your area, and then you plan the subsurface investigations accordingly. Now, geophysical surveys and core drilling are the two most common subsurface investigations which are carried out. Today, I'll be taking up some of the case studies. These are really fascinating case studies. I mean, in so many years, I was actually fascinated by, when I got those geophysical results and then I did the correlation with geological mapping data and the drilling data. I was like, wow. It was really very good. So I'm really happy to share those case studies with you today. So you get the subsurface investigations and done, and then this is the step that I'm talking about, the integration of the data, subsurface data with the surface geological mapping data, and then you develop the entire 3D geological model of your project. So without wasting much time, because I don't have much time, I'll quickly take up the first case study. Here the geological feature are the lineaments. Okay. This is the location of the upper reservoir of a particular project, and this is a quartzitic terrain. And you can see this is a satellite view of that. This is a Google Earth imagery of the area. And you can see these northeast, southeast aligned lines, right? All these parallel lines are called as lineaments. These are nothing but manifestation of stress release, okay, the tectonic stresses. And over a period of time, through the geological period, lot of weathering and erosion, basically these are subjected to continuous weathering. And that is how they have become so pronounced. So these are very easily discernible in a satellite imagery. So this was the most prominent set of lineaments. The second set is east-west aligned. You can see this is a bit less prominent and less frequent. Also, the frequency was also lesser. Now, you can also see there is a streak of vegetation along these lineaments. Okay. Now, when these lineaments were checked on ground, these areas were checked on ground, they actually saw that a lot of soil and vegetation was there at the locations of these lineaments, whereas on the other adjacent areas, the bedrock was available close to the surface, almost, at the surface, and there was just detrital material there. No vegetation, no thick vegetation, no large trees. So there was quite a vegetation contrast. And this is how the physical, the examination of the lineaments was carried out. Now, during the DPR stage, these lineaments were not investigated. All the drilling was carried out through vertical holes. Now, because these lineaments are also vertical in section, none of the drill holes had intersected any of these lineaments. And they thought that because this intermediate ground contains excellent, very good rock, so they thought that throughout the reservoir area, the bedrock is very good, but that was not the case. So it was decided to examine these lineaments through drilling, and a couple of cross holes were conducted. These cross holes established the width of these zones of lineaments, and as expected, they got completely weathered to very highly weathered rock in those stretches, flanked by good rock, slightly weathered to moderately weathered rock on the either side. So, based on the drilling, about 20 to 25-meter thickness of these lineaments was developed, but drilling could be carried out only at a couple of places. So then it was decided to investigate them through geophysical surveys because we needed a continuous view of the subsurface. So this is one example of just one profile which was conducted, and try to understand that obviously the geophysical lines were planned in such a way that they were perpendicular to the strike of the lineaments, so as to intersect as many lineaments as possible in one profile. So as you can see in this profile, these three weak zones can be identified near surface, and the depth of these zones extend to about 20 meter or so from the surface, and the lateral span is also about 25 meter or so. Now, upon combination of multiple profiles, when 2 or 3 profiles were combined together, we got the entire picture, and this is how the multiple lineaments were seen in the geophysical section, and these perfectly matched with the satellite imagery or the ground observations. And you can see we could estimate the depth of weathered or bedrock that could be expected along these lineaments, and we also found out we could also number the lineaments, their spacing and everything based on these geophysical survey. This is the ERI survey which was carried out. Now, later on, when the actual project excavation or the construction started, and we again visited the site, and we found that there was a vertical section, and this is how those lineaments actually looked in the in the vertical section. You can see this is the completely weathered rock in the stretch of about 15 meter or so in this particular case, flanked by slightly to moderately weathered rock. And here the depth of the exposed section was about 10 to 12 meter, but it was initially estimated to be about 20 meter, but later on it was found that it was close to 10 to 15 meter or so. And it was tapering down. The width of these weak zone was tapering downward. So this was a very classic case study where the geophysical survey was utilized to understand this subsurface feature. Now, the second case study was again very interesting. In one of our projects, we found there was inversion of resistivity, because generally what we see, most of you must have seen that we get low resistivity near surface, and as you go downward, you get higher resistive data. Higher resistive strata, because on the surface you expect loose soil or topsoil, which generally has lower resistivity. In this case, the top overburden was superficial, it was null, I mean close to zero, hardly less than 1 meter or so, but we were getting a very good competent layer at the top. And then suddenly, at about 20-meter depth or so, we were getting a layer with low resistivity. And then again, as we went down, we could see that, okay, we are again getting a competent rock. So we were really baffled. I kept discussing this with my teammate, and initially we were really confused that we couldn't understand what was the problem with it. And it was not just in one of the profiles, there were three parallel profiles, and in all of them, we got same kind of model. So, so very soon, drilling was followed, and the drilling confirmed this particular subsurface picture, which was deciphered by the geophysical survey. There were two holes drilled, cross holes, and we found that the top layer was sandstone, the middle layer was shale, and the bottommost layer was limestone. The limestone and sandstone are quite competent layers, whereas the shale is the weakest of the sequence. So that weak rock layer was, it actually corresponded to the shale layer, and this limestone was also known to be cavernous. So we did detailed logging of these holes and all, and we actually found out that the interface of shale and limestone was quite prone to cavitation, and weathering was observed at this contact, and there were clay pockets also. That means there were some cavities which were then filled back by the clay, which was generated by weathering and deposition of the overlying shale strata. So this shale was in a very bad state, and close to the limestone, it was totally, I mean, it was completely weathered. Above it, it was in the moderately weathered to highly weathered category. But as we went down towards limestone, then again, limestone was very, very good. It was very competent. So it perfectly fit with the geophysical picture which we had got initially. So this is how the drilling confirmed the geophysical section. Now, there was another case where, based on the regional geology, a fault was suspected near the upper reservoir. Now, it was decided to carry out some geophysical surveys to, just to find out if there are any traces of the fault. So, on both sides of the expected location of the fault, the rock was same. So during geological mapping, we couldn't really see any evidences of a fault as such, and a lot of part was covered with vegetation. So it was a bit difficult. But geophysical surveys gave us a very good picture. It showed some linear weak feature, and then it was further investigated through cross holes, followed by geophysical survey. The drilling again didn't give very good information about the fault as such, although we found some broken rock in this part, and on the other side we found a better rock. So somehow it was going along with the story of the fault, and then it was decided that we'll keep the upper reservoir sufficiently away from this fault line, the suspected fault line. So these were the two lines which were conducted close to that location of the fault. Then this I have already told you. Then again, at other location in the same project, ERI surveys were carried out along the lower dam axis, and what we found was another weak feature which was not intersected in the drilling. Here the drilling was carried out previously. The drill hole was conducted somewhere here, and the hole was drilled somewhere here, and the hole intersected somehow moderately to highly weathered rock, but it was not that bad. And the hole was vertical, so we never intersected this weak zone. So, but the geophysical survey clearly gave an indication of a weak feature, and so this has been kept in consideration that okay, there is a weak feature across the dam axis. Although this has not been investigated further, it is planned to be investigated in the pre-construction stage. So this is it. I mean, it has not been, we have not reached the conclusion for this particular fault as yet. So I'll just summarize what I have been working so far on is that understanding of the geological model of the project area should be your foremost aim for any geologist. And then it is like, putting all the pieces of the puzzle together. Okay, you keep posing questions, you keep looking for answers, and the moment you get the answer, you just you put that piece in your puzzle, and then slowly the entire picture emerges. But you have to have patience, and you also have to have, uh, you know, uh, what do you say? A vision that what you're looking for. As Sanjay sir also said, you have to know the problem, and that is often the most, common problem that people don't know what they are looking for. So if you have a targeted aim, you have a target, then you can actually decide which tool you are going to use. Okay, and so geophysical survey is a tool which is to be used in association with other investigation methods. Like I explained, it is to be, we integrated it with drilling data, with mapping data. Like in the case where I showed you that shale bed, it was not mapped during geological mapping because it was all weathered and covered with vegetation. We couldn't see it on the surface, but it was intersected in the drill holes. It was indicated in the geophysical data. Then we added it in our geological model, although it was not found anywhere during geological. So this is how you keep on, improving your model based on the data that you acquire from all the different investigation methods. So it should never be used as a standalone investigation method. And again, you can use it at any stage of project development. As I gave you the example, the first example was of the pre-construction stage. During DPR stage, those lineaments were not studied or not identified. And the second case study which I showed you was of the DPR stage investigations. So it is basically not written anywhere that you have to do this, or the geophysical survey should be done at any particular time. Whenever you have a problem and you think a geophysical survey can provide you an answer, you should go for it. So I think that is all that I had to say. A little something that I have experienced in while working on those projects that I have shared with you. So I guess I'll invite now Sanjay sir
Thank
to
you,
take over here.
Mugdha.
Yeah.
It was not little, it was very profound, honestly. You
Thank you.
covered through these case studies, the entire picture so beautifully, and congratulations for doing that.
Thank you.
Because this is so important to see how the entire thing is being put together. And almost your closing statement is very profound that most of the time we don't understand the problem altogether. So if we define the problem, half of the problem is solved, much like life. Right. In life also, our problems can be really solved if you're able to define the problems properly. So, all right. So now we'll quickly go to question and answer session, which is very important. So all the questions have been flowing in. I'll read the questions one by one. First is from Mr. Vijay Nagri saying in PSH projects, selection of reservoir at lower as well as upper site is of prime importance. So what are the effective geophysical methods to check permeability of reservoirs, landslide risk around reservoirs and waterways? So as we discussed, that last slide which I had shown, when we are talking of a reservoir, if you're detecting things like lineaments and these kind of things, ERI has been proven to be very, very effective in that. Whenever we are choosing a method, first again we have to define the problem. What are we looking at? So if we are looking at these kind of features which will make some change in the resistivity, then we will choose the resistivity method. If we are looking at certain features which will make changes in the strength of the rock, we will choose the strength based method. My suggestion always is to combine the methods. When we come to reservoir rim, the slope stability, as we have covered in that one slide, MASW, ERI, and seismic diffraction. This combination works best when it comes to slope stability. Not only in PSP projects, we are doing number of slope stability projects around the world, and these three methods as a combination are giving great results. Then Mr. Sumit Mazumdar, once you find some discrepancies by geophysical methods, do we substantiate it by drilling at those points again? So this question came in the very early stage of the webinar, so I'm sure it must have been answered by by now, Mr. Mazumdar. Geophysics is just one part of the entire sequence of investigation, like Mugdha also said. We are starting with even available satellite maps, regional geological maps, then engineering geological mapping, then going for geophysics, and then going for drilling. Okay, drilling is absolutely mandatory because geophysics is giving you physical properties. As she showed you one particular example: high resistivity, low resistivity, high resistivity. What are the formations there? That can only come from drilling, but drilling at the right place, not random drilling. So drilling after geophysics is the right way of going about it. Of course, we have to substantiate by drilling. Mr. Rajbal Singh is saying, what is the maximum depth of investigation and accuracy? So investigation depth for different investigations are different, of course. As I said, that if we are talking of GPR, we are talking of tens of meters. We are talking of seismic diffraction tomography. We are talking of in the range of 100 meters, right? If you're just using hammer 25, 30 meters, you go for weight drop 60, 70 meters, go for explosive, you can go for 100 meters, even more than that. Like to be very theoretically speaking, Russian scientists have used seismic diffraction tomography to map Moho, which is at 29 to 30 kilometers down. But they use nuclear sources. We are not going to do that, of course, right? Practical terms, we are talking of 100 meters, right? ERI, you can go up to 300 to 400 meters. Seismic tomography, practically, there is no limit. Like up to whatever depth you can drill your hole, you can investigate up to that depth. Go to things like helibone surveys, you are going to 600 to 700 meters depth. Going to passive seismic tomography, we are doing for oil and gas exploration. We are going up to 20 kilometers depth, 20,000 meters from where earthquakes are originating. Go for seismic reflection. We are going to 4 to 6 kilometers, which is being used for oil and gas exploration, can be used for tunnel route investigation also. Different methods, different depth of investigation to be chosen based on what we are looking at. Resolution will go down as you go down, all right? So you will not have the same resolution which you have the top. You will not have the same resolution once you're going 300 meters down. That's the most important thing to understand. Mr. Karma is saying how far the geophysical is possible and feasible to cover whole hydropower components, especially in very high variation of topography. Suppose in Bhutan, HRT aligns along very rugged and difficult terrain where it comprises huge cliffs and steep slopes. So how it's feasible to carry out geophysical tests covering whole area to provide complete information? It's a very good question, actually. So depending on the terrain, you have to choose your method. As I gave example of the Bhutan, this particular project which we did, for this cavity detection. Once I went for the site visit, I realized that no surface geophysical method were possible. The only platform available to us was a 20 meter by 20 meter platform. Of our depth of investigation was around 200 meters, right? So we did these drill holes to do seismic tomography there. Similarly, if you are, for example, doing a tunnel study and your terrain is very rugged, you have helibone time domain electromagnetic, where you're not going on the ground anyway. You're flying, and even in the tough, rugged terrain, you can acquire data. In Bhutan, actually, it has been done almost a decade back. So tough terrains have the solutions. In India, we have worked on certain PSP projects for the water conductor system, where the terrain difference was very high and slopes were very steep. We have in our team rope climbers. The team leader has done Mount Everest, actually. And that is the level of their training. Now, we use rope climbers to go along these slopes to put geophones and electrodes and things like this, right? So it is possible. The only thing is your effort will increase, but anywhere it is, mostly it is possible. Some method will be found out to solve the problem. What method, we have to decide based on the terrain. Then Mr. Furkan Safdar, what is the maximum investigation depth of seismic diffraction tomography? I just answered that, around in the range of 100 meters. Mohammad Nadeem Yunus, how many lines and what orientation will best capture subsurface structure? That's part of survey. That's part of survey planning. Okay. You plan your survey based on what structure you are trying to delineate, what is the dimension and depth of that structure, and accordingly you put your lines, right? So that is completely the part of survey planning. Mr. Egbo is saying ERI is such a subsurface revealing tool. What is the maximum depth of penetration in MASW? So active MASW is limited to around 40 meters. Okay, then you go to passive MASW or refraction microtremor, and then you can go around 100 meters. That's passive, because active is creating more higher range of frequencies. Passive is working with much lower range of frequencies. Lower frequencies will go deeper. 100-meter is the max which you can take by passive MASW or REMI. Then Mr. Thakur, Kshitish Thakur, how do we optimize treatment of major shear zones intersecting the dam axis, balancing excavation, grouting, and structural measures, while ensuring stability and seepage safety in complex Himalayan geology compared to more stable peninsular rock conditions? So, Mr. Thakur, although I can attempt to answer this question, but that won't be correct as a professional, because we are investigation professional, right? We are into imaging, right? So we are doing X-ray, ultrasound, right? Then the case is referred to the doctor, who decides how the problem is to be treated. So it is not right on my part to get into a domain of the treatment experts, to be very honest, right? But if you write to me on my email, I will answer to you also. I'll connect also to the right people. Mohammad Nadeem Yunus, can ERI reliably define bedrock level for foundation design? So, Mr. Yunus, that's a very good question. One of the best question I would like to answer. Choose the right method for the right purpose. All right. Simple thing is that rocks generally have higher resistivity. So the common sense says, why can't we use resistivity for rock delineation also? But that's not the right approach. For bedrock determination, the right technique is seismic based technique, because it is based on the strength of the material, P wave velocity or shear wave velocity, SRT or MASW or whatever, which tells you what is the strength of the rock, whether it is fractured, jointed, weathered, etc., etc. If you try to use ERI for finding the rock, in few cases you can be successful, few cases you can terribly fail. For example, basalt in India has low resistivity. If you're trying to use a resistivity method in a basaltic area, you'll be surprised that you'll not be able to detect your bedrock using that. Okay. Although if you go through the IS code, the old IS code, which is now being revised, and I am putting this point in the new IS code will show basalt resistivity into thousands, right? In central India, that's not the case. Basalt resistivity is much lower, and it is very confusing. Choose the right tool. Seismic refraction is the right tool for bedrock. ERI, in few cases it will work, in few cases it will fail you. So always combine methods. Is there any anomaly to differentiate meta sandstone and quartzite by Mr. Sunil Datta? So Mr. Sunil Datta, again, same question and same answer. It is part of survey planning. Out of both the formations, which physical property will have maximum contrast? Will it be resistivity? Will it be seismic velocity, which is directly linked to the strength? Choose that and accordingly choose the method. What is the maximum distance of boreholes to do seismic tomography by Mr. Bharun Giri? Yeah, that's a very frequently asked question. Now, it depends on what kind of source you are using. In Bhutan, we use explosive source. So the maximum distance between borehole was around 115 meters. Okay. If you're using a sparker source, these days we have just acquired one very, very strong sparker source. We are able to go up to 60, 70 meters. We have not tried more than that, right? It will also depend on the competence in the rock. If the rock is competent, you will go much farther. If it is loose, you will go much narrower. But generally try to keep borehole distance in the range of 50 meters to be safe, even with a strong sparker source. Okay, till the time we try higher than that. We have just tried up to 60 to 70 meters with the sparker. With explosive, we have tried up to 115 meters. Sunny CD also had the same question of the cross hole distance. I have answered that. Then Mr. Shadur Shan Sevraj, sir, is the grouting only option? We have to fill the subsurface caverns and cavities? Well, again, I am not an expert in that field. Treatment is not a domain I like to get into. Then Mr. Ilham Abla. One question, please, maybe not directly related to presentation. When people pump out deep groundwater, do you believe that there will be serious settlement of the ground surface? Well, it is not related to the presentation, as you very correctly said, but the common sense basically says that it will completely depend on the formations there. If the formations are loose, susceptible to settlement, settlement can definitely take place by withdrawal of groundwater. Can you please elaborate rock mass characterization using seismic diffraction? So there are basically, the tables which are available. Work has been done on this, where you can have the rock mass characterization based on P wave velocity. Barton tables are available readily if you just go and type for Barton or write to me. I'll share the Barton table, which does this correlation of rock mass. Then Maridu Ramakrishnan, for preliminary survey of dam sites locally in hilly region with highly undulating topography, which type of method of is generally most suitable? So, Mr. Ramakrishna, as I said, it will be chosen based on the exact site condition and the objective. Broadly, the methods like seismic refraction tomography, electrical resistivity imaging, and MASW, these are combined for any kind of terrain which you are talking about. Mr. Ahmed Yusuf, did you use IP to differentiate between clay and saline water, which have almost same low resistivity? In our geophysical exploration department, we have different equipment. How we can cooperate together? So, Mr. Yusuf, definitely. When you are talking of clay and saline water, which have the same resistivity, IP is the one which is used to differentiate between them. We have done them in many projects, and you're more than welcome to write to me. So Chetna ji will just write my email ID again in the chat box. Please write to me. It would be a pleasure to cooperate. Mr. Amit Kumar Verma, thank you for highly informative presentation. I know this question is not directly related to presentation. As geophysical methods are capable of exploring subsurface conditions, I was wondering whether they can also be applied to identify the existing foundation details of structures. In our case, we have several old bridges for which found yes. So there is one IS code. Sorry, not IS code. IRC code. IRC code, which in which I was a committee member, primarily authored by me. It was for bridges. First section deals with the new bridges, and the second section deals with the existing bridge foundation details, right? So it is definitely possible. Number of methods for that. If you send me an email, because just now I see the email ID has been put there, write me an email. I'll share with you all the details on that. It's not related to presentation. Never mind. I will send it to you. Then Mr. Sanjeev Sapkota, for high dam project around 200-meter, routing galleries are planned. What would be the preferred elevation difference for SRT investigation so that all geological information shall be covered, and this information will be helpful planning of curtain grouting later. So, Sapkota sir, I will again request you to please send me the drawings, the plan drawings at my email ID. I'll be very happy to look at these drawings and give you a detailed response to this. Mr. Swapan Mohanty, can geophysical methods help visualize grout impact without WPT? Of course. If you are doing grouting in any structure, if you have data before grouting and after grouting, it shows beautifully what has been the impact of grouting. Even if you don't have the pre-grouting data, at least it will show you whether the zone of weakness which you grouted has been actually treated properly or not. Mr. Vikas Tripathi, do we have an estimate how much electricity downward water will generate and how much electricity we will need to pump the water upward? Well, that's a very PSP question, to be very honest. I won't be able to answer that. Sorry. Ashok Kumar Singh ji, without project name, case study remains. This I have answered Ashok ji directly in the chat box. We have limitations. Both I and Mugdha, we have serious limitations. We are working for different clients. We work on their projects. And even if you are a client on a particular day, you would not like your data to be shared on any webinar or any conference. So we cannot name the project. It remains extremely relevant because what we are trying to show is that how different methods are being used to understand the subsurface in different conditions. Rakesh Mehrotra ji is saying, don't we require drilling for geological mapping for Mugdha? So I'll let Mugdha answer to this, but I'll again remind you of the sequence which we talked about.
Could you just repeat the question?
Yeah, I will. So sequence was We are going with all the available satellite images, geological maps, then going for geological mapping, then going for geophysics, and definitely drilling is important, very important. So the question, Mugdha, was, don't we require drilling for geological mapping?
No. We require mapping for planning our drilling. And later on, based on the results that you get from drilling, if you want to again confirm something, then you can have a second round of mapping. Mapping is ideally should, it should keep going as long as the construction of the project also, continues. So, but first step is mapping, definitely.
Thank you, Mugdha. Then Mr. Rakesh Mehrotra is saying, will you need geophysical investigation after reservoir fill up to no weaknesses? Ideally, it should be done before the reservoir fill up. Okay, if by any chance reservoir has been filled up and you are having certain issues of seepages or water loss, etc., then geophysics definitely can be used to identify these points, but it will be much more difficult than doing it before the reservoir is filled up. Mr. Abla, question from, once we know the subsurface situation, who will follow the result for the design? Geologist, geohydrologist, civil engineer. So generally, Ablaji, after that, it's a team of engineers and geologists. They sit down together, and design engineers are involved in the entire process. They do that. Sabin Tiwariji, based on your experience, what is the difference between ERI and bathymeter test? They are totally different tests, Tiwariji. Bathymetry test is something basically which is based on echo, that is sound waves. It is sending the echoes inside the sound inside, getting reflected from the bottom of your lake or the reservoir, and it is giving you the depth of the lake bottom, etc., etc. ERI is based on electrical resistivity, that is electrical currents, and it is giving you subsurface information. If I'm supposed to do ERT near the bank of larger than 1,000-year-old river where the overburden contain densely stacked boulders like quartzite, granite, etc., underlying the weather weaker phyllite rock, how can we easily distinguish that these overburdens are not overburden and not the bedrock? As I assume the resistivity of quartzite being higher than phyllite rock, one will get confusing. Yes, of course, one will get confused. I have not gone through the entire description, but I just know this. If you're trying to interpret a complex geology based on just one method, there are 90% chances you will fail. That's why we always, for last 30 years, have been insisting on combining methods. When I started working in hydropower projects in the country, the golden era of hydropower projects, that was 98, 99, 2000, 2001, seismic refraction was the most common thing to do. Even the boulder beds show very high velocity. If you are doing only P-wave investigation using seismic refraction, you will not be able to differentiate between the boulder bed and the rock. As soon as you bring in REMI, that's the time I started using REMI for that. You are able to differentiate between boulder bed and rock because shear wave velocity of boulder beds is much, much, much lower than the rock. And I told clients we must do this together. They said, no, just one method because we don't want to spend too much. I used to do REMI from my side for my own confidence. Client was not paying for it. So similarly, for any investigation, always combine method. If you're just choosing one, you are going to be having problems, right? So since you're talking of boulder beds and rock differentiation, always combine a method which is based on, let's say, shear wave velocity. You will be able to differentiate. Revati Ramanji, what geophysical techniques are used to detect shear zones and faults along HRT alignment, and how can geophysical data support slope crystal analysis in reservoir rim areas? This was answered in my table. The presentation will be sent to you again. But reservoir rim, as I repeated later also, MASW, SRT, ERI. Similarly, for HRT alignment, you can do ERI because it can go deeper and find out what's down there. Hussain Beg Sab, Iftikhar Hussain Beg Sab, could we get water quantity information using ERI like in LPH, GPH, etc. before drilling? ERI is definitely affected a lot by presence of water, right? So you can have an estimation. I won't say quantity, but estimation of where the higher water content is there, where lower water content is there. Mr. Dhananjay, what are the best geophysical method of mineral exploration? Okay, this webinar is going in a different direction altogether. All right, mineral exploration methods are slightly different. We have gravity, we have magnetic, we have IP, we have resistivity, we do SP. So different kind of methods depending on which mineral targeting you are doing. Okay, and few methods are directly targeting a mineral. Few are indirect. That is, they are giving you about the structures which are conducive for a particular mineralization. So separately a different topic. Write to me. I'll send you an entire book I have created on mineral exploration using geophysics. I'll be happy to share it with you, but drop me a mail for that. Mr. Bhuvan Pandey, which geophysical investigation has to be carried out in 60-year-old earthen dam need to get actual drawing also? So, Mr. Pandey, earthen dams, I have investigated almost 140 dams in the country till now, and most of them have been earthen and masonry because they have the largest population. A combination of electrical resistivity imaging, its seeming potential, MASW is great for earthen dams, right? So that's something which do. But if you are really interested in this topic, please join the webinar next month, June 6th. That is exclusively on dams, right? So we'll talk about it there. Okay, Mr. Tashi Dorji. In Bhutan, we are currently carrying out DPR of one of the large PSP project with deep-seated underground powerhouse, about 800-meter deep from surface. We are doing deep borehole and also exploratory drift, but these will take longer time. Any possibility of geophysical test to support the location of underground powerhouse without having to wait for completion of ongoing borehole drilling and drift? Important from Bhutan. So, Tashi Sab, to be very honest, whatever we have discussed till now, if we are going so deep, 800 meters, primarily seismic tomography is the technique. Okay, and but we can look at other ways of doing things, right? But I'll need some more detail from you. So just write on my email ID, and I'll try to get more details to you. Mr. Mainak Ghosh Roy, what are the geophysical investigation carried out so far finalizing slope stability for deep pit powerhouse? Slope stability, as I said, MASW, refraction, and ERI, that's the combination which is required. Mr. Kshitish Thakur, in the context of pumped storage projects, how should smart investigation strategies differ between geological complex Himalayan region and the relatively stable peninsular India, particularly for underground cavern siting and long-term slope stability? I think this question we have answered a number of times already. Every project is different, it's unique, and based on the geology of the project, we need to choose the right tools. Survey design is very important, which always has to be done based on geology of the project. That's why Mugdha is here today. Mr. Manoj Kumar Dangwal, what kind of test can be used to study reservoir-induced seismicity in fragile rock? Best regards. So when we talk of reservoir-induced seismicity, of course, you have to do monitoring. So we have this strong motion, monitoring, which is done to understand how the seismicity is changing with time. So you have to install these stations. Then Tushar Karmakar, in case high rapid, fast flowing, very high noise of river, what should we do? Can seismic without blasting work? Well, fast flowing, very high noise, so seismic is a problem. But you can use noise-based methods. For example, you can use REMI, which is based on noise itself, and try to use that. Again, more details required. Okay. Dear Dr. Rana sir, what is the maximum depth at which GPR can detect underground utilities in the urban tunneling projects? Best regards, Mr. Manoj Kumar Dangwal. Urban areas, 6 to 7 meters is the maximum depth I have seen GPR working. Anyone can claim 10 meters, 15 meters. They are trying to sell GPR to you. So don't go by that. I've been doing GPR in this country since 1996. Long time, actually. So 6 to 7 meters is the max in good ground conditions. If you go to bad ground condition, you can go to 2 to 3 meters, not more than that. Okay, then I'll just quickly see if any other question is related to Mr. Arishma. I'm sorry, I shouldn't say Mr. Arishma is asking, can we use repeat geophysical surveys, that is time-lapse ERT or microseismic monitoring to monitor seepage, deformation, or reservoir-induced changes over time? Yes, whenever you're looking at changes over time, time-lapse methods do help, of course. So yes. Okay. What should be the ideal survey grid spacing for a PSP project? No, there's no general thumb rule for that. Survey design has to be done based on the objective which we define. All right, and the questions keep coming. I'm so sorry, but it's already 4:34. So we are already late, but there are a number of questions, and I'm sorry, but we'll have to close it now. What I'll request you is please drop me these questions, whatever have not been answered on this platform, by email, and I'll reply to each and every question because time is important. We had around 300 people here and almost equal number of people joined on the YouTube channel. I don't want to waste time for anyone, but do write to me, and we will definitely get all the answers to your questions. No answer will remain not replied. And before we go, I would request Rashik ji to please put everyone on the screen. I'll request everyone to open their cameras so we can take a few group photographs. And these group photographs are very important for our memory. So Rashik ji, we can please put everyone in the grid. I still see myself. Is that normal? Yeah, that's great. So Chetna, you will be taking the photographs, screenshots. Okay. There are 10 screens you have to take today. Everyone, please remain with your face on the screen so we can see you smiling. And I can see few smiling faces on the screen right now. Navani Saab is there, Rajbal Saab is there, Edward Flint is there, of course. Miss Gaurav is there. They're all known faces I'm talking about. I respect all of you, but these are the people we keep meeting very frequently. So it's always good to, it's always lovely to see them like this. And so Chetna ji, you can tell me when you are done taking screenshots. And you can unmute yourself. Now the webinar is over. No problem.
We can still make out what she's
Yeah, I
saying.
know.
She's
Exactly.
very expressive.
Lip reading, yeah.
I know you guys are good in lip reading. No gender discrimination, but there are certain strengths you have as a particular gender. So we
This has
surrender.
been positioned
We,
as a strength. Nice.
we surrender there. Absolutely, it's a strength. It's a strength.
Good
Yeah,
evening,
a
sir.
lot of screens to be captured today. People,
Good
bear
evening.
with me.
I have a suggestion, sir. Am I audible?
Yeah, you're audible. Please go on.
So, in fact, this smart preliminary, you were asking that how much of the project weightage we are using for investigation of the project. So it is mostly less than 1% because CA guidelines are also like that. Some they are not giving this the preference. Can you have that because you are in the matter of membership and all that? So this should be raised in the form like that. We should increase the investigation. So once the failure cost will be less. So so yourself being the members of the various organizations and all that. This is the important question to give the most weightage to the investigation part of the projects, especially hydropower projects, which are having the most gestation periods like 20 years, 10 years. We can come reliably decrease that gestation period by doing the smart investigation, by putting in the effective cost. So the percentage of the cost should be high. So this is my suggestion.
No, this is absolutely correct. And to be very honest, I'm not aware of CEA putting any ceiling on the investigation which you can conduct.
Yeah.
Or
There is a ceiling.
there is a ceiling. There is a ceiling.
There's a ceiling.
Okay, I have no idea because as I understand, if I'm the
There's
project owner,
CA guidelines. If we want to have this thing to go through the CA guidelines, there are every this component of the DPR guideline. So this investigation part allocate less percentage to this. But wildlife investigation, this should be given the preference and the weightage should be increased. This is my suggestion if you go for that.
No, I totally agree with you, Nagri Saab. You are exactly saying what I always say and I dream of. I always say
Yes, sir.
increase the investigation. The only thing what I was trying to put across was that if I'm a project owner, let's say I'm Adani or I'm Greenco, right? I'm making a project where I'm putting thousands of crores, right? I personally think that CA is not going to stop me from spending money on investigation. They always tell you what is the minimum investigation required to be done, right? They cannot say that you can't do geophysics here, you can't do extra drilling here because we as CEA will not allow you to do that. That's what I mean by ceiling. Okay, there is no ceiling on what you want to spend on investigation. The problem is that as project owners, we want to always save on the money on investigation, despite knowing that we'll pay a very high price later when the surprises will crop up, right? But your
Yes,
point is very well
yes,
taken. At different forums, we keep talking about it, that investigation
yes,
should be
sir.
given their due share. Absolutely.
Sir, if I can,
Thank you,
I
thank
can
you.
just
Okay.
add one line, just I'll take few seconds, that it is many a times, especially the PSPs which I've been working currently, what happens is the timeline, there is a lot of pressure that we have to finish the jobs and so timeline. So it is not always about the money. It is mainly that, okay, we don't have time, whatever investigations we have, just summarize them, make out the results based on them. It is something like that. It is the hurry of, the developers are in a hurry to finish the project. So that is why they're not giving enough time for investigations. That is also happening. It's
That's
not just
a
that they don't
So
want to
that
spend
that
money.
that that mindset has to be changed. This is my personal opinion, because once we go, that mindset is changed from the developer's point of view. So they feel that we are unnecessarily investing the money in investigation part. So that mindset has been changed. That will be beneficial for the developer in the longer run.
Absolutely. That mindset has to change, and that's where this particular webinar is even more important because we are talking about much faster way of doing smart investigations. Okay, because this
Yes,
is
yes,
geophysics is
yes.
the fastest way of covering large areas and then optimize drilling. So it basically pays both way. You make it faster, you make it optimized, and you have more information. And this discussion can continue for the entire night.
That's
So
that
so
that. So,
so now I'll say thank you very much,
and
Suchetna.
towards the
Suchetna
end of
has
that, I want thank you, thank you.
Suchetna
So
has taken
thank
the
you, sir.
pictures.
Thank
She is showing thumbs up. And thank you all for joining. It has been a wonderful afternoon with you, or morning if you're joining from other countries, or late night if you're joining from other countries. So it has been wonderful to have you and see you on June 6th again. And
Thank you,
Thank you
sir.
till
so
then,
much.
Thank you.
Thank you.
Thank you, Sanjay sir, for this opportunity. Thank you so much.
Mugdha, thanks for your presentation. It was wonderful. Thank you very much.
Thank you, sir.
Thank
Thank you,
you.
man. Thank you.
Thank you, sir.
Thank you, sir. Thank
Thank
you.
you very much.
Thank you, sir.
Thank you. Thank you, sir.
Thank you, Ronald.
Thank you, sir.